Alright, good afternoon everyone. Just before we kick off the class, I'd just like to remind you of our two primary rules for today. So our first one is no hand, no speak. So if your hand's not up, I don't want you to be calling out. And the second one is two-way respect. So I show you respect if you're talking, I'll listen and pay attention. And vice versa. If I'm talking, I want you to just pay attention, not do anything else distracting. So, to start off with, can anyone tell me what the topic for today might be based on the picture up the top? There's just one of those per person, not everyone.
Yeah, that's it.
Well, no, but like just you're the only one in this class. It's not all four of you are playing up.
But I'm a good
No,
student.
they're all different.
Oh, are they?
Yeah.
Okay, he just... Alright, cool. Disregard. Yeah, can anyone guess what the topic for today might be based on the picture up the top? Tuscany.
Horror. Rose.
Horror. Good assumption, I like it, but not quite. Anyone else? Last one. Sorry, that was Rose. Tuscany.
Looting?
Good. Very, very close. So today we're talking about buoyancy. Yeah, I spelled that right.
Oh.
Buoyancy. So specifically we're going to talk about Archimedes' principle, and I'll explain what that is in a minute. So can anyone tell me why things float? Rose.
They're light, so they rise to the top of the water. They're not too heavy, so they don't sink.
Very good explanation. So one way of thinking about it is if this is my swimming pool, has anyone noticed that if you swim to the bottom, you feel that pressure pushing in on you? So that's density or pressure. So down here, pressure is large. Up here, pressure is small. So as a result of this pressure difference, this being larger, it squeezes on you, so it kind of like pushes you up towards the top of the water. And that's why things float, because the pressure below the surface is more than at the top of the surface. So, in physics, when we talk about buoyancy, I would use the symbol FB, which is the force from the buoyancy force. Does that make sense to everyone? Okay. So, let's see who was paying attention to last week's class. Can anyone tell me the name of the Greek physicist that I mentioned in last week's class with circles? So that's with an A. Is that a question, Nathan?
The answer, Aristotle.
Not quite, but good answer. He is Greek. Very close. Do you have a guess, Rose?
Archimedes.
Bingo. Good. Archimedes. Archimedes. And more specifically today is Archimedes' principle. So this came about in ancient Greece in a town called Syracuse. There was there was a general by the name of Hero, spelled as you see there, and he assigned a blacksmith. Can you hold on to that, please, Anthony? Assigned a blacksmith to build him a golden wreath. I've got a little demonstration of what his wreath might look like.
Ooh.
And not long after he built the wreath, there was rumours that the blacksmith had ripped off the general and had replaced some of the gold with silver. So the general hero at the time assigned his cousin Archimedes to come up with a way to test whether the crown was actually made of gold or whether it had silver in it. But being a very valuable item, he obviously couldn't melt it or add chemicals to it or anything like that. So he had to think of a way to test it without changing or damaging the crown. So that night, Archimedes went home, was sitting in his bathtub, just going through his usual routine, and then he had this epiphany, and he came up with this idea. And at that time, he yelled out, "Eureka!" and he ran all the way home completely naked, yelling out, "I found it, I found it!" He was a bit of an eccentric guy. And that's where Archimedes' principle comes from. So, Archimedes' principle, I'm going to hold on to that one. So I'm going to write it down, so you don't have to copy this, I've just got it on paper, and I'll get you to copy in a minute. So Archimedes' principle states that
if one of your pick a particular element on the table, it is very easy to hide stuff on its own. You just label it there so you don't forget the next time.
the mass of water...
Did you need another one? You didn't have yours from last time? I thought you said you had it out.
displaced by an
That's
object.
alright.
Anthony, what's our second rule?
Two-way respect.
Are you showing me respect right now, Anthony?
Okay. Sorry, Mr. Ross.
That's okay, Anthony.
Yeah, and we went through the actual structure of an atom. Is anyone confident enough to come up and draw that, or would you like me to draw that for you? No? I'll draw that up over here.
Oh, sorry. Okay. So, Archimedes' principle. The mass of the water displaced by an object is equal to the buoyancy force on it. So what this means, using some diagrams, if I've got my big jug of water and my little jug of water, and I get some mass, and let's say this has got water in it. Obviously, if this was all the way to the top, if I put something in it, the water's going to overflow, right? Same as when you get in a full bath. So the water that overflows into this thing, what Archimedes' principle says is this mass is equal to, say, 2 kilograms. If I weigh this container, I've got 2 kilograms of water in. That means that this force is equal to 2 kilograms. Does that make sense to everyone? Any questions? Anthony?
That mass, the little protein mass.
The little beak. Oh, this mass?
Protein mass?
Yes.
Is 2 kilograms.
Good question. So, yes, if the object floats. So in this case, my serious mass is floating on the surface. So the buoyancy force is exactly equal to the mass of the mass. If it sinks, it's a slightly different story, which I'll get to in just a second. So, using this concept, this is how Archimedes tested the crown. He knew what the mass of gold should be, knowing how much gold he was given. So, he took the crown, put it in the water, and then measured how much water came out of the container. And then he compared that to the mass of the gold, and he actually found that they were different. So the blacksmith had actually ripped off the general in this case. So like you mentioned, Tuscany, if we have an object that doesn't float, let me just rub this off. So if I took this and I hung it from a scale, say, and this mass is equal to 5 kilograms, just in the air. If I then move it into my container, hang it by the scale again, and according to the scales, it equals 3 kilograms. Can anyone tell me what the buoyancy force might be? 2!
Alright. So last time we went through this, we went through our structure. We determined that
Any guesses?
2 protons and 2 neutrons is helium.
Tuscany? Hesitant?
3?
3? Not quite. So think about, this is how much it weighs. Now the scale is telling me this is how much it weighs.
2.
So it was the
Tuscany?
2.
2, exactly. So now, oh god, sorry. Lieutenant. Equals 2 kilograms. So Archimedes' principle still works because the water that came out here
Now we did a couple of
into my container now weighs 2 kilograms. So it's still the same. The amount displaced is equal to the buoyancy force, but if the object sinks, it's not. It doesn't displace enough water for it to actually float. Is that okay? Last question I'm going to leave you. If I have a 1-ton block of iron, I'll just draw a big, and a 1-ton bowl of iron, both the same weight, both 1 ton, both made of iron. Do you think they'll both float? Will neither of them float? Will one float and one won't? What do you think? Hands up if you've got any guesses.
1 flow and 1 won't.
Sorry?
1 flow and 1
You reckon which will float? The bowl? You reckon the bowl will float? Alright, does everyone agree with that? Anyone disagree? No challenges? Exactly right. The reason for that, they're the same mass, right? But I've got a little block of iron here, it's quite small. So if I chuck that in water, it only displaces an amount this big. But if I've got my big bowl,